Hello, everybody. So today I'm going to talk a little bit about a monitoring framework that we use. There are some similarities with last talk, and I will go over initially some of the motivations that we've had for working on developing this monitoring framework, as well as some of the enhancements that we have added in the past year. So this framework was initially developed by Jesse Martinez, modeled after IBMON, that was originally written by Susan Coulter at Los Alamos National Labs. The goals that motivated us to work on this project further was collecting better port-level traffic counters on both switch and network cards. And we also wanted to be able to pin those counters to specific jobs. And so we also collect the linear forwarding tables from the switches. And the majority of our big clusters at Los Alamos National Labs are OmniPath. And so primarily focuses on that for this monitoring framework. And we wanted to integrate into our existing monitoring architecture. And so we set out with the goal of going after a higher granularity because the existing state of HSNMon when we started this project was default to about 30 minutes, and it ran at about a minimum of 1 minute. And so we wanted to get to 10 seconds or under. So I'll talk a little bit about the architecture of this application. It runs as a daemon on the dedicated Fabric Manager node, and it fails over with the Fabric Manager. This is a collection of scripts that checks various error conditions, running the fast fabric tools that are provided by Intel, including OPA extract perf. That's the tool specifically for gathering the transmit and receive counters. And the way that this works is it sends all of its messages to syslog. And from syslog it goes to a, we have some data analytics clusters that are used, and I'll get into some of the details of how this changed later. So there's a collection of scripts. There's a main script that runs as a daemon. It's configurable. You can set which error conditions you want it to send messages on. You can set it to run at different frequencies. It will execute other scripts, including this HSN Rosetta code. And what that does is it collects the counters using OPA extract perf and parses it into a readable format for the administrators. And then it will also look up the local and remote devices so that you get an accurate idea of what ports this data was sent and received to and from. Additionally, there are a few more scripts. We have HSN counters, which will dump the counters and clear them to a file, HSN moninit, which does all of our configuration setup and definition of shared functions. There's also fabric status, which pulls FM information to determine if it's the master, otherwise it goes to sleep. This allows for seamless failover as we run our clusters with at least a couple of standby fabric managers. Additionally, there is create netmap, which will generate a map of the different links on the fabric. So before we started on enhancing this project, this is the flowchart defining basically how the framework worked. On startup, it would daemonize itself, check if it was a master. If not, it would go to sleep. If it was master and not paused and not on DST mode, then it would just run as normal, and DST mode allowed slight variation in the way that it functioned so that we could maintenance the supercomputers at times. This provided an interface that allowed you to either run on startup as a daemon or execute a startup script. You could run stop, start, status commands DST start and stop, as well as pause and clear counters. So the goals that we set out at the beginning were put into place so that we could make some modifications to achieve what we wanted to. The big challenges that we faced were that the minimum amount of time that it took to run this program was over a minute on our target clusters, our largest OPA clusters. Additionally, the underlying fast fabric tools that were used for collecting the counters were themselves too slow for our purposes. OPA extract perf, for example, takes over 10 seconds to run on the size of clusters we're targeting. And so, therefore, we couldn't use it for our purposes. Additionally, at a higher granularity like that, we ran into issues with timestamps being inaccurate because of the way that the performance manager and Intel works. Essentially, the performance manager will query all of the ports on the fabric, and it will save the sweep time and the sweep duration. However, getting that information using the fast fabric tools as one operation isn't possible the way the tools are designed, at least as far as I could find. Additionally, syslog at the volumes that we were using, sending performance counters, it just fell over. It wasn't possible to run syslog for that high frequency. So in order to take on these challenges, we separated out the performance gathering into a separate process and rewrote one of the Intel tools using the OPA management API. And using those tools, we were able to directly query the performance administrator and sub-administrator within the OPA fabric manager so that we could get tools or get data at much higher granularity. This also allowed us to, at the same time, get the sweep time and sweep duration so that way we could have accurate timestamps when we were making calculations. In order to overcome the syslog issues that we ran into, we started using AMQP, and we have a RabbitMQ server and a data analytics cluster specifically for analyzing the data that we get out of this. So the new tool that I was alluding to is called Get Port Counters, and this essentially just pulls the port counters and an accurate counter time. And this is different than what it replaced, which is OPA extract perf, in a big way, in that it continuously pulls to check to see if a new image has been created. An image is created anytime the performance manager sweeps the fabric. And so if a new image is created, it will output all of the data in a predefined format that I'll show on the next slide. Additionally, I created a tool for sending data via AMQP directly to our data analytics server. And then also I created a tool for comparing the difference on the output of the last linear forwarding table. This allows us to just check anytime the switch's forwarding table has changed, so that way we can pin jobs to specific ports via their routes. So this is a sample output of what the command would provide. This is just a couple of lines on a small cluster, and you can see this is showing an edge switch, and it has the ports, and you can see the image start and duration, as well as the image ID. Transmit and receive data is also shown in megabytes, and on the data analytics side, we then use the timestamps and the difference in transmit and receive counters to calculate how much bandwidth was actually consumed. At the bottom of there, you can just see anytime it pulls and finds that a duplicate image from the last time, it'll just skip and not run again for the defined pull frequency. And the defined pull frequency is provided as an argument to the command. So this is that same flowchart just showing the changes. So HSNMon now provides the ability to save the linear forwarding table for data analytics, pinning bandwidth consumption to jobs. as well as forks to create the separate process for the high frequency performance counter gathering. I won't get a whole lot into the data analytics, but this is just a picture of our dashboard. We're calculating the rate based on the image start time, and you can see this is, I believe this is primarily just switch-to-switch ports. I don't have the legend shown here, but in our Grafana dashboard, it shows exactly which nodes are producing that bandwidth consumption. So future work in addressing this and continuing to work on this is deploying this across bigger clusters. We currently have it running on a couple of clusters right now. The granularity we have on one of our test clusters is currently at 1 second, and on a different cluster that's a little bit larger is at 10 seconds. It's kind of limited by how fast the performance manager is running, and we have yet to still do testing on jitter. But essentially, running this at higher frequencies is just querying the performance manager, so whatever jitter would be caused by the performance manager itself. Further work includes the ability to track when the performance manager times out. This is interesting because the performance manager works by pulling all of the switches and the nodes in the fabric. And if a certain amount of time passes, probably due to congestion, and the performance manager hasn't actually heard back from a node or switch, the counter will not be updated, but the image start and duration time will be updated. And so there is the possibility of data inaccuracy due to that. Additional further work is we're planning on making this open source so that other people can criticize it and tell me I'm terrible at coding, and no, just so that we can all, be a better community and everybody can share it and use it. Additionally, we're hoping to apply these lessons learned to InfiniBand in our IB-Mon scripts so that we can have better data there. Obviously, just because the majority of our clusters are OmniPath, that's where we started. Additionally, there's the opportunity for sharing code and the potential for using a Perf Manager event plugin with OpenSM for gathering these counters. I hope I haven't been keeping anybody from supper. Do we have any questions? Yes?
Isn't it kind of tough to get specs timed out with the setting manager doing all the parsing and sample?
So you're asking about the ability to parse at a fast enough speed?
Yeah.
Is that correct?
And also the fact that everybody's sample is going to be a different rate. Sometimes there might be 1 second here.
Right. So you're talking about the duration of the sweep?
Yeah.
With that question? Okay, great. So the question is, how do you deal with the difficulties, I'm going to paraphrase, how do you deal with the difficulties of the sweep duration time and the fact that every time you gather the counters, you don't have an exact timestamp, you have a duration in which that timestamp was collected in? Is that fair? Okay. So that's a great question. I'm going to back it up a couple of slides. I'm not going to pretend I haven't been losing sleep over that. So you can see right here, we have the image duration, and that's showing 108 milliseconds, doing some spot checking with clusters. On the biggest ones, I've seen it get up to 120, 150 milliseconds. And so this can be problematic, especially if that number gets higher. And so the idea is by tracking that and actually collecting that with every single time we sample, we can know if we get too high a number that we have to essentially throw away that image and just get the average for calculating the bandwidth over a larger period of time. Additionally, we can do a little bit of uncertainty propagation to figuring out when we're calculating the bandwidth consumed, how much error are we actually getting in our end values. And I have the calculations on that in my office, but I figured that'd be a little boring to put in a slide. Does that answer the question? Did you have, kind of? Okay, we can take more offline if you want. Any other questions? All right. Thank you very much.